Good questions, all. Thank you, Wes. And we will get on to the next, which is presentation number 6 in today's session. It's by Abhijit, Khare, and the subject is design and analysis of cryogenic cooling system for superconducting motor.
Hello and welcome. My name is Abhijit Khare. I am a senior research specialist with the Center for Future Energy Systems at RPI in Troy, New York. I am also a doctoral candidate in electrical engineering at Virginia Tech. My presentation today is on the design and analysis of a cryogenic cooling system for a superconducting motor. I would like to acknowledge the ALSET lab under Professor Luigi Vanfretti here at RPI and NASA for supporting this research. I would also like to thank Wolfgang Stautner of GE Global Research and Joshua Feldman and Peter Shaw at the University of Illinois Urbana-Champaign. This is a brief overview of my presentation today. I will start with the motivation behind the project, describing our team and our project. I will then provide an overview of the superconducting motor. This will be followed by a description of the cooling system concept and the analytical design. I will then move on to the representation of the system in the software Dymola, which uses the language Modelica. I will end with a summary of current steps and future work. This slide describes our team and our project. The Center for High Efficiency Electrical Technologies for Aircraft, or CHEETAH, was established in 2019 under the NASA ULI program. CHEETAH aims to bring together experts from the fields of aeronautics, electrical systems, and material science. We have a multi-institutional team of universities and industry groups with government collaboration through NASA and the AFRL. Our project is focused on the development of technologies for a fully electric aircraft. The aircraft uses liquid hydrogen storage with a fuel cell system to power the superconducting motor. Liquid hydrogen is used both as a fuel and as a cryogenic coolant medium here. One of the reasons for using a superconducting motor is the increased power density, which is important in a weight-sensitive application such as an aircraft. This presentation is focused on the cooling system, which uses liquid hydrogen to cool the superconducting motor. Here is an overview of the machine that will propel the aircraft. Superconducting motors are electromagnetic alternating current synchronous machines that use superconducting windings, where conventional machines use copper coils. Advantages include reduced size, lower rotor losses, and better weight to power capacity ratios. It is necessary that the superconducting motor operates below a critical temperature, or it would revert to its normal phase due to exceeding of current, temperature, or magnetic field limits. CHEETAH uses an outer rotor design where the armature coils are on the stator and the field coils are on the rotor. The magnetic field on the rotor is contained by the shield coils. This is done to avoid usage of bulky ion shielding. Low AC loss MgB2 superconducting coils from Hypertech are used that have a critical temperature of 39 degree Kelvin. Though lesser than other superconductors, the losses are still in the order of around 4 kilowatts. Minimal losses of 1 to 10 watts are also observed in the field and shield windings, but for the cooling system design purpose, the focus remains on the armature coils. As mentioned on my previous slide, the stator is on the inside and the rotor is on the outside. In the figure on the lower right, single-phase liquid hydrogen enters as a liquid, absorbs heat from the armature coils, and exits as a two-phase mixture. The propulsion fan spins at 3000 to 4500 RPM. 4 kilowatts of heat is rejected in the stator, while the rotor has heat rejections of around 1 to 10 watts. Firstly, we have to calculate if this motor can be cooled by the amount of hydrogen we have on board. Using enthalpy of vaporization of liquid hydrogen and assuming 20 to 30% available to cool the motor, We calculated that with 16 motors and a power capacity of 1.66 megawatts per motor, we get an available cooling budget of 4.3 kilowatts per motor and a liquid hydrogen boil-off rate of 9.66 grams per second per motor. The cooling concept for the armature coils is given in the figure on the top right. The MgB2 coils are bonded to an aluminum heat sink, which also act as mechanical support for the coil. The coil will release heat into the heat sink, which will transfer heat into the pipes containing the liquid hydrogen. Liquid hydrogen will absorb the heat, partially boil off, and exit as a two-phase fluid. Here is a topology of our cooling system. For a small length, the inlet pipe is contained within the outlet pipe. The inlet pipe goes to the end of the design where the flow splits into multiple tightly wound helical pipes. As the liquid hydrogen flows through the helical pipes, it absorbs heat rejected by the armature coils through the aluminum heat sink. At the end of the helical pipe, the multiple flows converge into the outlet pipe. The field and shield coils too reject minimal heat, which is absorbed by the aluminum structure and conducted through the rotary bearings to the coolant. The entire structure is in a vacuum vessel. The field and shield drive the propeller. The lower right figure shows a CAD rendering of the schematic system that I just described. The first figure shows an individual pipe, followed by tightly wound wall-to-wall helical pipes, followed by the aluminum structure encasing this, and then the armature coils. There are certain advantages to using helical tubes for heat exchange. Centrifugal forces in a fluid flowing through a curved pipe cause secondary flows circulating outwards into the core region of the pipe to form a pair of symmetrical vortices. The combination of main and secondary flows creates a flow pattern in which maximum velocity is shifted outward from the center of the tube. The secondary flow produces a transverse transport of the fluid over a section of the pipe. This additional convective transport improves the heat transfer between the fluid and the wall of the pipe, but also increases the pressure drop compared to a straight tube. To calculate the heat transfer capability of a helical pipe, the first calculation that's needed is the Reynolds number. This is a function of the diameter of the coil, that's small d, and the diameter of curvature of the entire pipe, that's capital D. If this value exceeds 2300, the flow is turbulent, and based on the geometry of our current design, the flow regime is turbulent. Next, the effect of friction is considered through the factor zeta, which is a function of the Reynolds number Re, the diameter of the coil small d, and the diameter of curvature of the pipe, that's capital D. An approximate value within 10 to 15% of the Nusselt number is calculated by applying the Schmidt equation, which is a function of the tube geometry. The Reynolds number, the Prandtl number, and the mass flow rate. The Prandtl number here is a function of the fluid temperature. The mean convective heat transfer coefficient alpha can therefore be calculated using the Nusselt number, tube diameter, and lambda, the thermal conductivity of the fluid. As explained previously, this method improves the heat transfer but also increases the pressure drop. Pressure drop is calculated by breaking the tube into a series of bends. The local pressure drop coefficient is a function of friction coefficient zeta, the velocity of the fluid, and the density of the fluid. Zeta is a function of the geometry of the tube, which gives three distinct ranges for the coefficient K sub Re, and A1, B1, and C1, which respectively are the coefficients considering the angle of turning, the radius of curvature, and the effect of elongation on the curvature of the cross-section. Shown here in the figure is a mathematical model of the cooling system using the multi-domain modeling software Dymola. A stock model of this thermal model of a synchronous AC machine was modified to account for the stator windings, that's the armature windings, being superconducting MgB2. The model considers thermal models for the stator, the air gap, and the rotor. The design being an outer rotor design, this model was modified accordingly. A helical tube model was added to this as the heat exchanger. The tube dimensions were parameterized to match the actual design. A separate cryogenic media model was also developed and tested for phase change to match the working of the Cheetah superconducting motor cooling system. As shown here in the program parameterization window, the medium was set to LH2. It's a little hard to make out, but the fluid properties, you can see that the medium was set to LH2 using a cool prop solver. The heat transfer flow regime was set to turbulent. That's the third line in the heat transfer section. And the pressure drop regime was also set to turbulent. That's the fourth line in the heat transfer section. The geometric parameters were input using the helical pipe input parameters shown there. And the mass flow rate was also parameterized to be controlled from the outside. Currently, work is being done to simulate this model to validate if the 4 kilowatt heat can be siphoned off and if the 4.3 kilowatt cooling budget as calculated is enough at a 9.66 grams per second boil off rate. The pressure drop values are being analyzed to validate a particular mass flow rate. An inverter model is also being developed so that test cases can be run for a power flow from the battery to the motor inverter setup and from the fuel cell through superconducting cables to the motor inverter setup. Future work involves a hybrid mode test where both the battery and the fuel cell supply power to the motor without overloading the motor in terms of voltage. Following this, the model shall be integrated for electrothermal testing. Um, I would finally like to again acknowledge the work we conducted by Wolfgang Stautner, who I work with, and would also like to acknowledge the efforts of Dr. Feldman and for the figures courtesy both Josh and Kiruba Haran from the University of Illinois. Thank you. If you have any questions, feel free to ask them.
Great job. Thank you very much. And I would like to say that it's really exciting to see these two areas coming together at last, liquid hydrogen management and superconducting motors.